Swayam Prabha. Digital India. Educated India.
volume dV. So rho into dV is equal to, sorry, let me write it here. So this part is equal to your dV. Okay, so rho into dV is your mass. So this becomes equal to m by 3. This becomes equal to m by 3 into L squared plus H squared. Okay, so this is how we have got Ixx. Now you can similarly you can compute Iyy and then Izz. So we can get from Ixx, Iyy and Izz. Similarly, we can also compute the cross products of inertia. Okay, so what we are going to do is I will just write down so you can compute and see yourself. Iyy is equal to m by 3 into w squared plus h squared, and Izz is equal to m by 3 L squared plus w squared. Okay, now what about the products of inertia? Now let's look at the products of inertia. Ixy is equal to 0 to h, 0 to L, and 0 to w. And here it is xy rho dv, which is equal to triple integral of 0 to h, 0 to L, 0 to w. And here we have xy rho dx, dy, dz. Right? Now when I integrate this first with respect to x, what do we get? With respect to, first I integrate with respect to x. So what I get is 0 to h, 0 to L, w squared, okay, which is with respect to x by 2 y rho dy dz. So this is the first term I get, integrating with respect to x. Then I integrate with respect to y. I get 0 to h, sorry, this is 0 to h, 0 to h. Okay, I get w squared L squared. So y becomes y squared, and the limit is 0 to L, so it becomes L squared by 4 rho dz. And then finally we get the same logic again. So we are getting m by 4 w into L. Okay, now so from here, when we're integrating, what are we getting here? Now please remember that the volume dV is equal to w into L. Okay, w into L into h, that's my dV, and into the density rho makes it equal to dm. That is where my dm is coming from, where my m is coming from rather. Okay, this is equal to mass. So this is my mass, okay, where it is coming here. Okay, so this is equal to w m by 4 wl. Now similarly I can find for the other terms, Ixz is equal to m by 4 into hw, and Iyz is equal to m by 4 hl. Okay, so putting all the terms together, we can get out the inertia tensor. Now something to note here is that we have made the assumption that our axis is here. Okay, that is my axis. This is my y, this is my x. So x, y, and z, that is my axis. But in the case of the manipulator, the axis need not be exactly there. The axis could be shifted. For example, it could be a little bit shifted to this point here, and this is my axis. Okay, so in the manipulator case, this could be z, and this could be sorry, my x is here, x, y, and z, or it could be in the center of the link. So basically, it will not be at the edge of the link, because when we are having a manipulator like this, so this is my link, the axis will be somewhere here. Okay, so the axis will pass like this. So this is not exactly on the edge, so it is having some distance from x and y. So for that, what we can do, we can use the parallel axis theorem. Okay, so we can use the parallel axis theorem. Okay, in case the axis is shifted again. So by using the parallel axis theorem, Izz, for example, is equal to Izz plus m into xc squared plus yc squared. Okay, so we can simply use the parallel axis theorem, and for cases where for example, in this particular case, if you are saying that the axis is passing through the centroid x and c, so then I put it like this. Okay, so now we have a way of finding the inertia tensor of the body, and also we have a way of using the parallel axis theorem such that we can make adjustments for the change in change of the axis. So in this particular case, the origin is at center of mass. Okay, so in this particular case, the origin is in center of mass. Now, so this is one way of finding the inertia of a body. Now let's look at let's proceed with our study of dynamics. Now here what we are seeing is that a robot manipulator is moving in space, okay, and there is going to be propagation of theta and theta dot, theta dot and theta double dot will start moving, and it is going to move like this, and forces will come backwards. Now there are different ways of there are different methods rather of computing the dynamic equation of dynamics. One could be Lagrangian Euler. One is Lagrangian Euler. Lagrangian Euler method. Now Lagrangian Euler method is basically an energy method. Okay, so this basically forms okay, we'll come to it. So this is Lagrangian Euler is an energy based method. Then there is Newton Euler. Now Newton Euler is basically force based. Okay, so these are methods of computing the dynamic equation or formulating the dynamic equation based on Lagrangian Euler or Newton Euler. So first we'll look at Lagrangian Euler, then we'll look at Newton Euler. Okay, now going back, what is the objective of all this that we are doing? We have a motor which is actuating the joint. Okay, so at here there is a motor which is actuating the joint, and when the joint moves, it creates a velocity, and the velocity propagates. Now we want to find what is the torque acting at the joints. Okay, this is what is of interest to us. Now in order to find the torques at the joint, we need to find what are the sum of all the forces that are acting on the joint. Now what are the different kinds of forces? There are inertia forces. So dynamics is dealing with inertia forces. Okay, plus there is centripetal force. Okay, because the link is rotating. Plus there is Coriolis force. Plus there is gravity forces. Okay, so the total torque, which is what is the objective of dynamics here? The objective of dynamics is to find what is the torque acting at the joint. Okay, that is what is tau here, tau 1, tau 2, tau 3 when the robot is moving. Now why do you need tau? Because you need to find out what motor is to be put on the joint to support that kind of torque. Okay, and this tau is equal to the inertia force. So inertia forces are because of the inertia. Okay, this the linkage will have it's a rigid body, it has mass, it has inertia. Then there is centripetal plus Coriolis. So you can imagine here that when this is rotating, so there is one link which is rotating on another link. So suppose I put it like this. Let me just draw two of them, one here and one here. So when this is rotating with a velocity theta 1 dot, this could be rotating with a different velocity theta 2 dot now. Okay, so it is like this rigid body, which is this link, has another rigid body which is rotating with a different velocity now, a different angular velocity. So basically it will be subjected to a Coriolis force also. So it is like a body here, and there is something which is rotating on it. So this is also rotating and that is also rotating. Okay, and because of the differential rotations, angular velocities, it will have a Coriolis force. Now there is a centripetal because this is rotating. Okay. Okay, so what we were looking at is the forces that the torque is made up of. What kind of forces? Inertia forces. So inertia is because of acceleration, centripetal and Coriolis force, plus there is gravity which is acting. Okay, gravity is always there, which is pulling the link down. Okay, so gravity is acting in that direction. So there is gravity. Okay, so plus there can be other forces. There can be other forces. What kind of other forces? Friction. So friction can be there. There can be external force, J transpose F. Suppose there is a force acting there. Okay. So that will also cause a torque at the joints. So the inertia, so the total torque is based up, is an addition of all the forces: inertia, Coriolis, centripetal, Coriolis, gravity, friction, and so here we are not going to find friction force, and we are going to neglect this one also, external loading. So we'll find what is the effect of this only. Okay, so now let's look at the Lagrangian Euler way of finding. So Lagrangian Euler method. So this is an energy based method and this energy based method in which we basically we make a scalar function called the Lagrangian L, which is the difference of the kinetic energy and the potential energy. Okay, then we put it in this equation, d dt of dl by d theta dot minus dl by d theta, which is equal to torque. So for all the links, we find the kinetic energy, then we find the potential energy, and then we find this Lagrangian scalar function. We make this scalar function L as the difference of the kinetic energy and potential energy, then use this equation to get the torque. Now that is the way the Lagrangian Euler method works. So let's look at a very simple example of this before we proceed. Okay, so a very simple example of this is given here. So we have a link which is we want to take a very simple example to start off with. So let's look at the simplest of the simplest examples. So we have a single link, 1 dF. Okay, this is a simple one. Now we have a motor which is connected to a gear, and this gear is connected to the link. Simple case, simple 1 degree of freedom system. Okay, I want to derive the dynamic equation of this system. Okay, 1 dF. Now how do we proceed? So first thing that we do is we find the kinetic energy and the potential energies of this. Okay, so what we do is let me write down JL is the moment of inertia of this one. JL is the inertia here. Now theta m is the motor angle. Theta L is the link angle. So this side is the link. Okay, this is the motor, and in between there is a gear, and the gear ratio is n. So when the motor rotates, the gear rotates, and then the link rotates, and it has only 1 degree of freedom. Okay, so now the link is equal to 1 by theta L is equal to 1 by n theta m. Okay, so the motor speed has to be reduced and the torque has to be increased, right? So the torque acting here is tau m is this side. Okay, that's the motor torque, and the torque on the other side is tau L. Okay, so now we have a 1 degree of freedom system, a motor which is driven by which is actuating a gear, and then it is driving the 1 degree of freedom link, and there is a gear ratio of n. So theta L is equal to 1 by n theta m. N is a reduction gearbox. Now what is the kinetic energy? So the kinetic energy K is equal to half mv squared. So we know K is equal to half mv squared. Okay, so what is this equal to? Is equal to half Jm theta m dot squared plus half JL theta L dot squared, that is half mv squared. Okay, so we have written our kinetic energy, which is equal to half, and we can take theta m dot squared outside, okay, which is equal to Jm plus JL by n squared. Okay, so Jm by JL from here we can get it. So theta L dot is equal to 1 by n theta m dot from this equation. Okay, so theta L squared is equal to 1 by n squared theta m dot squared. So from here I replace this here and I come here. Okay, so now what we are doing is we want to find the potential energy. So the potential energy is equal to, let's call it V, which is equal to mgl into 1 minus cos theta L. Now if you look at this 1 degree of freedom link, where is the reference? Okay, suppose I draw the side view of this, okay, from this view. So this is my link. Okay, now if I take that to be 0, that is horizontal, but that is not 0, right? The 0 is down here. Okay, so what I need to do is I need to find, if this is my L, if this length is L, let's call it L. Okay, that length is L, then this is my L. So how much it has gone up, okay, from here, from this position is given by this much distance. So it is equal to 1 minus, or L minus L cos theta. Okay, so if you look at this, let me draw it again. So what I'm saying is, when you're looking from this side, okay, what would this link look like? This link is like this. So when it is pointing downward, and I say this is my reference 0, 0, okay, this is my reference 0 for potential energy. So potential energy reference is 0 here. Then when it is going up like this is my L. So how much it has gone up? It has gone up by L minus L cos theta. Okay, this is my theta. Okay, and that is L. So it has gone up like this. Okay, so how much is that? So L minus L cos theta. It has gone up like this. Okay, how much is, by how much it has gone up? It has gone up by L minus L cos theta. Okay, so this is essentially because I'm taking my reference to be here. Okay, it has gone up by this much now, L minus L cos theta. This is equal to L, the length of that link. And that is how I get mgl 1 minus cos theta L. Okay, so that is how this is coming. Now I can convert this also to mgl into 1 minus cos theta m by n. Okay, so I have converted this also to theta m. Why? Because there is two variables you see in this equation. Okay, there's theta m is a variable, theta l. So I converted all the theta l's to theta m. Similarly, here there is a theta l and a theta m. I converted all to theta m. Okay. Now, what we are doing is we can find the Lagrangian, make the Lagrangian L is equal to k minus v. Okay. So we know what is kinetic energy. Kinetic energy is this term. What is potential energy? Potential energy is this term. Okay. So kinetic energy minus potential energy, if I write, then L becomes equal to half Jm plus Jl n squared, and this is theta m dot squared minus mgl 1 minus cos theta m by n. Okay, that is kinetic energy minus potential energy. Then I take it and I put it in this equation, d dt of dl by d theta m dot, okay, minus theta l by theta m is equal to tau. So the variable here is theta m, so I'm writing theta m here. Okay. Now if I put it into this equation and write, what do we get is Jm plus Jl into n squared. Okay, theta m double dot plus mgl by n. This is equal to sine theta m by n is equal to tau. This is my equation of motion of that one link system. Okay, so what we have done is we have found this equation of motion of a one link system by using Lagrangian Euler dynamics. Okay, now this is one link, only one link. So there you have inertia forces, which is this one, so which you can see is mass. So inertia is equivalent to mass into acceleration. So mass into acceleration is here. This is the inertia forces. So this is my inertia term. Then this fellow is my gravity term. So mg is there. So mgl is the gravity term. There is no centripetal or Coriolis force because there is only one link here. Okay, so no Coriolis and centrifugal. Please note that. Now let's move on to another problem where we have a 2 degree of freedom system. This was 1 degree of freedom, extremely simple. Now let's look at a 2 degree of freedom system and see how we can solve it using Lagrangian Euler. We just have to follow the principle of Lagrangian Euler, otherwise everything is very, very simple. Now this is example number 2. So we have a revolute joint like this. This is my revolute joint system, and there is a prismatic joint here. Okay, let's say this one is a 2 degree of freedom system now. One is a revolute joint, then there is a prismatic joint. Okay, so this first joint here is a revolute joint, R. This one is a prismatic joint. Okay, so this fellow is a prismatic joint, it's a P. Okay, so there are two variables. Theta 1 is a variable here. Let's put our dh parameters. Okay, so I can put my z0, z1 here. So x0 is there and x1 is here as per dh. So this angle is my theta 1. Okay, and let us say this is my m. So this is the distance. L1 is the distance from here to here. Okay, and this is a prismatic joint, so this can move back and front. So let me say this full distance from here to there, okay, is to here right till here is my d2. Okay, so this is my d2. So if you can visualize this robot carefully, this is looking very clumsy. Let me draw it again. So when we are looking at this robotic system, let me draw it a little bigger because this is difficult to understand. So this is one link. Okay, there is one more link here, which is a prismatic joint, and this joint is moving front and back. Yeah, now it's better, I think. So this one is a prismatic link. This is a first one is a revolute link. So let me draw the axis z0, z1. This is rotating like this. This is my x0. This is my x1. Okay, this is m1. This is m2. It is coming down as m2. Now the distance from here to here is L1, and the distance from here to there is d2. That distance is d2. Okay, now it's clearer. And what are the two variables? One is theta 1, and the other variable is this d2. Okay, so we have two variables, and this is a 2 degree of freedom system, 2 DOF. We have put dh parameters, so note this very, very carefully. Where are the axes and what are the two variables? Now we need to understand very carefully that where is the second z? Second z is this side, z2. Okay, and x2 can be put here. That's our second axis. Now understand this very carefully, that when this link rotates, when joint 1 rotates, what happens? It can rotate like this or like this. Okay, that's because of joint 1. And joint 2 is a prismatic axis, so it can only translate like this. It cannot do anything more. Okay. But because these two links are connected, this joint 2, this link 2, whenever link 1 rotates, link 2 will be subjected to forces because of the rotation of link 1. Okay. So what we are saying here is that although link 2 is a prismatic axis, whenever this joint 1 is rotating, it will have an effect on link 2 also. Okay, so link 2's motion is not independent. So this is what I was trying to talk about, that there is coupled motion and the motion of the joints are not independent. So this is an example where link 2 will be affected by motion of link 1. Okay, so for example, if link 2 is not moving but link 1 is moving, even then it will be subjected to forces. Okay, because the velocities are moving in the forward direction. Okay, so now this is something important to note, and let us start writing our kinetic energy and potential energy equations. So for the first link K1, so this is my link 1, that's my link 2. So for link 1, I write it as K1 is equal to half m1 L1 squared theta 1 dot squared, okay, into plus half IZZ1 into theta 1 dot squared. Okay, the now how did this come from? This came from, this is half mv squared, v is equal to omega r. Okay, so half where did this fellow come from? It is into v is equal to theta dot into L, right, that we know. So half mv squared is equal to theta dot squared into L1 squared. Okay, v is equal to omega r, that's where it comes from. So it is still half mv squared, where v is equal to this. Now the second one is half IZZ1 theta 1 dot squared. I'll just explain what is that I. K2 is equal to link 2. This is something we need to be careful about. M2, this is my M2, which is the mass of the second link. Now the second link is going to have one velocity because it's a linear velocity. plus it will have a rotating velocity of the previous link. So it will be subjected to two velocities, one of which is linear, the other fellow is rotating. Because of the rotation, it will also end up with a linear velocity only. Okay, so what we are getting here is because of the rotation of link 1, it will subject this link 2 to a velocity. Okay, plus it has its own velocity. So this is equal to its own velocity is d2 dot squared. This is the linear velocity because of the translating joint. Plus it will have a velocity because link 1 is rotating. Okay, so this will again be equal to d2 squared into theta 1 dot squared. This is the same as this. Okay, so that means v is equal to d2 into theta 1 dot. Okay, so half mv squared plus it will be half izz2 into theta 1 dot squared, because it is rotating. Okay, now the rotation is because of the previous link, so it is theta 1 dot. Now this link 1 and 2, they have inertia tensors. This is what we are talking about some time back. So it has inertia tensor I1, which is given as Ixx1 0 0, Iyy1 0 0 0 0, Izz1. So this is my inertia tensor for the first link. Now the inertia tensor for the second link is equal to Ixx2, sorry, Ixx2 0 0 0, Iyy2 0, this is 0 0, Izz2. Okay. Now if you look at the manipulator, this link has inertia tensor I1, the first link. The link 2 has inertia tensor I2. Okay. Now when it is rotating, it is rotating about which axis? It is rotating about z axis, right? So in the inertia tensor, we are going to look at this rotation about the z axis. Similarly, the translation is also about z axis. So that is the term that is going to be used, and hence you see that half Izz1, half Izz2 theta 1 squared is used because it is rotating about z axis now. Okay. Now we can write the kinetic energy. Now kinetic energy is equal to U1 is equal to m1 L1 g sine theta 1. In this case, we are assuming horizontal as a 0 reference, plus m1 L1 g. This is my what is called the compensation. Okay, why do you need to compensate it? You need to compensate it. You need to compensate because your reference is horizontal. So this is my horizontal. This is I'm taking as 0. Okay. So the moment it comes here, potential energy is actually not 0. Okay, because gravity is there. So gravity will pull it down. Okay. So in order to compensate for that, I'm saying m1 L1 g is there. So this is m1 L1. This is my g. So this is compensating because I've taken my 0 potential to be horizontal. Actually, it is vertical. It's not horizontal. So to make that compensation, we give this compensation term. So U2 is equal to m2g d2 sine theta 1, and there is a compensation here also, m2g d2 max. So the maximum stretching it can go, that is the amount of compensation we'll need. Okay, so this is m2g d2, and if you look at d2 is this length. Okay, that is my d2, and d2 max, because d2 is changing, so d2 max is the amount of compensation that is required. Now we put this kinetic energy and potential energy into the Lagrangian equation, but before doing that, what we do is we make a very interesting observation. Okay, that in the Lagrangian equation we can simplify it and write like this. What we see here now, this is a simplification or modification of Lagrangian Euler dynamic equation. Now what we see is it is d dt of dl by d theta dot minus dl by d theta is equal to tau. Now L is equal to kinetic energy minus potential energy, and kinetic energy consists of velocity, potential energy consists of position. So this fellow is made up of theta dot and this fellow is made up of theta. Okay, so this L, when we are differentiating with respect to theta dot, potential energy does not have theta dot, only kinetic energy has. Okay, so what I do is I write it like this, dl by dt into dk of d theta dot, okay, minus dk by d theta plus du by d theta is equal to tau. So this simplification I can make, and it becomes easier to compute. Okay, we'll see how. So basically what we are going to compute is each of these terms will compute separately, okay, and then we'll find the tau. And this is essentially done because L is the difference of kinetic and potential energy, and kinetic energy depends on theta and theta dot, and potential energy depends only on theta, and that is what we have done here. Okay, so now let us go and complete what we were doing. So we have completed the potential energy and the kinetic energy. Now I find my dk by d theta dot. Okay, so I actually take this equation one by one. I'll first take this term, then this term, then this term, then I'll take ddt of that term. That's what I will do. So kinetic energy is equal to the sum of the kinetic energy, which is equal to, so dk by d theta dot is equal to, so remember that this one has a theta 1 and it has a d2 dot and it has theta 1 dot. So we'll differentiate with respect to theta 1 dot first, then with respect to d2 dot. So what we'll get is m1 L1 squared plus IZZ1 plus IZZ2 plus m2 d2 squared into theta 1 dot. Okay, that is the first equation that we have to differentiate. So if you go back again, so you get k1 plus k2. So k is equal to k1 plus k2, and this contains theta 1 dot is there and d2 dot is there. So first we differentiate with respect to theta 1 dot, then with respect to d2 dot, and that is what. Similarly for potential energy also. So u is equal to u1 plus u2, and first we differentiate with respect to theta 1, then with respect to d. Okay, then with respect to d2. So theta 1 is also there and d2 is also there. So what we get is this term. Here it is m2 d2 dot. Okay, so this is the first term. Then dk by d theta, we get dk doesn't have the velocity term does not have theta 1. So again just theta 1 and d. So what we get is m2 d2 theta 1 dot squared. Okay, so this is the second term we get. The third term is du by d theta, which is equal to g into m1 L1 plus m2 d2 L2, and then we have cos theta 1. Okay, and then we have gm2 sin theta 1. Okay, so du, the kinetic energy, we differentiate again with respect once with respect to theta 1 and then with respect to d2. Okay, because both are there. Now and then what do we do now? We got to put it into this equation. What was the equation? ddt of we need to find dl by theta dot. Okay, this term we need to do ddt of dl by, sorry, dk by d theta dot. We simplified it. Okay, so it is dk by d theta dot we found here, and I have to do ddt of that now. So if you do the ddt of that and add the terms, what we do get is, so I put into this equation dk by d theta dot du by by d theta. That was my equation, right? So I simply take the previous one. So here if I do ddt, what will happen is this theta 1 dot will become theta 1 double dot, and d2 dot will become d2 double dot. Okay, but note here very carefully, something to note very carefully is that there are two variables actually. Theta 1 is there and d2 is there, both are variables. Okay, so when you're differentiating, what will happen, you have to differentiate first with respect to theta 1 dot, then with respect to d2. Okay, so there are two variables there. So if you do that, what will end up here is tau 1 is equal to m1, I'll write it in matrix form, okay, which is equal to okay, let me write it this way only, is equal to m1 L1 squared plus IZZ1 plus IZZ2 plus m2 d2 squared into theta 1 double dot. This is one we have got, plus because there is another term d2 is also there twice, so there is a twice m2, so there is a twice m2 d2 theta 1 dot, and there is a d2 dot. Okay, this I just explained that this equation, okay, this equation has this equation has, sorry, I have jumped too much. So this one has two variables, theta 1 dot and d2. So when you're taking d dt of this, okay, so when I'm computing this term, d dt of dk by d theta dot, what is going to happen is you'll have to differentiate twice, and what you'll get is the term plus 2m2 d2 theta 1 dot and d2 dot, okay, plus the other terms are already there, plus m2 d2 g into cos theta 1. Okay, so this term is already here. Now what about tau 2? Tau 2 is equal to m2 d2 double dot minus m2 d2 theta 1 dot squared plus m2g sine theta 1. Okay. Now what we see is that there are terms which are dependent on acceleration. So these are terms are dependent on acceleration here. Okay. Then there is a term which is a Coriolis term. So theta 1 dot and d2 dot. So this Coriolis term here. And there are terms which are dependent on g, which is just on position. Okay. So this, your tau depends on theta double dot, theta dot and d2 dot here, and theta. So it depends on acceleration, it depends on velocity, and it depends on position. And each of this is inertia. This is Coriolis plus centripetal. Okay, plus this is gravity. Okay, so what we have seen is that the total torque acting at the joints is the sum of inertia forces, Coriolis, centripetal force, and gravity force. And this is how we derive. This is very easy if you go step by step to understand how the torque comes. Okay, so this is how the, okay, so this is the simplification we have made of our equation in trying to first compute these terms and then taking ddt of that. It becomes easier. So this gives us the relation of the torques acting at the joints. Okay, so this gives us the relation of the torques acting at the joints of the manipulator. So let us stop here today, and we'll continue in the next class and look at examples of another example of Newton-Euler, and we'll also look at examples of Lagrangian-Euler. Now Lagrangian-Euler is good to implement in MATLAB because most of it is matrix multiplications, and hence it is sometimes preferred over Newton-Euler. Newton-Euler is essentially vector based, okay, whereas Lagrangian-Euler is basically matrix based because half mv squared is there. So we'll stop here today and continue in the next class. So thank you.